All right. Hello and welcome, everybody. My name is Marissa Bluestein. I'm an assistant director at the Quattrone Center for the Fair Administration of Justice at the University of Pennsylvania Carey Law School. You are here for a monthly program that we put on for folks who are engaged in post-conviction investigations and litigations of innocence and wrongful conviction cases. This series is sponsored by a cooperative agreement with the Bureau of Justice Assistance. To this month and next month, we have a double header with Dr. Jeff Salyards from C-Case. I'm going to get his information up here in just a minute. So this month we are talking about Dr. Salyards is going to give us some background information for how, when evaluating cases with forensics, we can kind of get a sense of what known and or potential error rates are, what they mean, and then next month in December we'll be applying those in the tool marks and firearms arena. But before we even get started, so you know, Dr. Salyards is the forensic research scientist at the Center for Statistics and Applications in Forensic Evidence, or CSAFE. But he has a very storied career within forensics. Dr. Salyards has did serve on the FFSB for several years. He has been the chief scientist at the U.S. Army Criminal Investigation Laboratory, as well as a principal with the Analytical Services. He has 30 years of experience in scientific leadership, investigations, forensic consulting, excuse me, and teaching as well. He has served as the director for operations and assistant professor at the Air Force Academy Chemistry Department, and was honored with the Outstanding Academy Educator Award. He holds his PhD in chemistry from the Montana State University, Master of Forensic Sciences from George Washington University, and has completed a fellowship in in forensic medicine from the Armed Forces Institute of Pathology. So, Dr. Salyards, we are so happy to have you with us, and I am going to turn it over to you.
Very good. Well, thank you, Marissa. I'm honored by those kind words. I think, though, it's just a reflection of the amount of gray hair that I have. I've been alive long enough to do many of those things, and I'm really honored to get to address this crowd. I think you play a really important part in forensic science. From our little world in forensic science, we may be the chefs in the kitchen cooking this stuff up, but I feel like you're the servers who are gonna, make the customers, make our stakeholders, you dictate the experience they have in this restaurant. And so it's really special for me to be here today, and I don't take this opportunity lightly. I'm going to share my screen. Very good. Looks like we're hopefully all looking at my first slide.
Yep, looks great.
Great. As Marissa said, this is part of a two-part series. And so ultimately, next month, we're going to talk about firearms and tool marks, and we're going to talk about what is the condition of that forensic science discipline, and how much do we know about error rates, accuracy, reliability, their overall validity. But that's a big topic. In order to do that, I think we need to first back up a step and just talk about what it means to meet that Daubert factor. And when we talk about things like error rates and validity studies, what does that mean from a scientific point of view? So let's I've noticed through my time in science that I think the Supreme Court might have even used the language like a mythic infallibility, right? When I don that white lab coat and I go into court or talk to attorneys or talk to judges, I think there's a sense that we're doing something really special, and we should be believed at all costs. For those of you old enough, you might remember the television show Gilligan's Island. And I was always struck by the role the professor played, right? He was an expert in everything from organic synthesis to language of, tribal headhunting groups in the area to the weather, whatever it was, he was an expert and he knew about it. And so how do we go from this situation, this sort of ipsy dixit, I'm wearing the white lab coat, I said it, you can trust me, and how do we get to really understanding what that means? How do we know what we know? So the presentation I'm going to give you today, it was part of a larger presentation I gave that took several hours, where we went through sort of each of the Daubert factors. And I just gave you my impression of what is it you're probably very familiar with what it's like to read that as attorneys. But when I read it as a scientist, there's some of what we read exactly the same, but there are other places where those words have different meanings to lawyers and to scientists. And so this is a great opportunity to kind of talk about it. Today, we're just going to take on two of these things. We're going to talk about this notion of testability. What does it even mean to have a testable claim?
Yeah.
I'd love to have stuff I don't need.
Yeah.
I'm sorry, Marissa, was that a question or a?
Nope, just a bleed over from the
No worries.
microphone, so apologies.
No worries. So we'll talk about testability, and then we will jump down to the third, or the fourth bullet, to the known and potential error rate. We could spend time on each one of these things. I think they're all interesting, but for our purposes today, and especially for where we're headed next month, those are the two things we really need to understand. So the first notion of testability, I feel like this is sort of the cornerstone of science, is we want to be talking about things that are actually testable. And so there's some really special ways we talk about that. Wolfgang Pauli is a very famous physicist and chemist doing quantum mechanics, and he criticized one of his colleagues by saying that's not only not right, it's not even wrong. And so when things are not testable, we get this sort of sarcastic tone in our voice as scientists that you're not even on the right playing field. So there are a few folks who came along and helped us understand that. One of them is Karl Popper. He wrote, like in the 60s, this notion that we have to have a falsifiable hypothesis and reproducible results. That if you don't have those two things, then we really can't even go further. You're not really even doing science. And so I thought I'd give you a couple examples that are sort of counterintuitive. First one, though, might make sense. If someone came to me and said, look, I'm very devout, I'm a man of faith, and I want you to help me to design a scientific experiment to inform the existence of God. And then they tell me that throughout these religious texts, there's evidence that water responds differently when God's around. But what I find when I review the text with them is in Genesis 6:17, we have a lot of water. We have flooding, water shows up, and that means that there's a God. And then later in Exodus 14:16, we find out that the water disappears in the Red Sea, and that means there's God. And then later in the New Testament, in Mark 4:39, we find out that if the water doesn't do anything at all, that also means there's a God. Now, I'm not here to criticize anyone who has religious faith. I come from a deep faith tradition myself, but I'm here to say, as a scientist, I would say there's no way I can design a scientific experiment with those claims, right? There's no way to falsify that. What does the water do that would say there's not a God? How do I falsify the claim? Now, the interesting point, though, is there are some things that can sound very superstitious, very pseudoscience, but they could still be tested in a scientific way. So one of them, Operation the Grill Flame Project, and there were other similar projects. This was with the Defense Intelligence Agency. The CIA was also doing similar things. And I want you to notice the date. This isn't like in 1943. This was in 1983, in a little more recent history. And they were researching remote viewing and extrasensory perception. Because, hey, if you're an intel agency and someone can look at a headquarters 2 miles away and tell you what's going on inside of that room, that would be fantastic, right? So how do we go about can that be testable? And it turns out it can be, right? I could get to people who claim that they have ESP, and we could come up with a falsifiable claim, right? I could say, do you have extrasensory perception? And then I could present you with this test and say, so you say you do. And I could say, all right, I've got some cards, I've shuffled them, and I put them face down here. So we got 10 cards. So I want you to take a guess. Is each card red or black? Now, for this to really be interesting, I'm going to just indulge me. I'd like you to take the test. I don't have you all so I can see you on screen. Just take out a piece of paper and either just randomly scribble down some R's and B's, some reds and blacks for the cards in each of those positions. If you have a stronger belief that ESP might be real, then do your best and take your best shot at this. And because I'm going to have you score your result, and we're going to talk about those results over the next few slides. So it won't make a lot of sense if you haven't actually done it and succeeded or failed. And so I'll give you just a second or two to write down 10 predictions there. All right, I'm going to assume that, that you've had a chance to do that. And now I'm going to reveal the right answers. So now, very importantly, I want you to score yourself. And this is where the chat will come in handy. I'd like you to put the number you got right in the chat, but especially let's start with, if anybody got 10 right, type the number 10. And then if you got 9 right, put in 9. And then 8 right, put in 8. And then 7, go ahead and type that in. And maybe 6. Very good. And then everybody else. And let me kind of open the chat so I can see here.
So say Jeff, it runs the gamut from
Yep.
2s, 3s, 4s up to 10.
Wow. Okay, so I like it. So we have a few 10s, right? So the interesting thing would be, certainly 10 is a remarkable score, right? And so the fact that we have a few 10s, does that mean that we can declare that extrasensory perception is real? And so part of this falsifiable claim, the first thing you begin to learn in science, and it's not always intuitive. In fact, it's easy to make the mistake we're about to discover here, is to see that provocative number. Wow, a couple of people got a 10, or a couple of people got an 8, and forget to ask this question. If everyone was just guessing, if there's no such thing as ESP, how many might they have gotten right on accident? And do our results differ from the accidental result in any profound way, right? And so, let's see, there we go. All right, so what might happen by accident? So what we find out is we've got a binomial distribution with 10 possible outcomes. We find out that you're going to get this bell curve, that even though the statistical answer, right, would be, if I'm guessing, it seems like I'd only get 5 right. Some people are going to get 6 right. Some people are going to get 4 right. Some people are going to get 2 right. Some people might get 10 right. And so if you've got a group of like 53 people, there's an 80% chance that at least 2 of them will get 8 or more right. I think this group, we did even a little better than that, right? So you want to have a situation where the result that you're seeing, so often in science, we talk about this notion of statistical significance. And that often means, is the thing that I'm seeing, would it happen by chance less than 1 time out of 20? Many mainstream scholarly journals have that sort of 5%, 95% significance level. More physics, chemistry journals, maybe they want that to be more like 99.1, right? That the chances of seeing this on accident would only be 1% of the time would you get this kind of result. So that's the first thing we want to look at is this testable? And once I test it, did the results really diverge from what would be expected from just random chance? The other thing we run into in forensics is some experiments that we want to do are too hard to do. They're testable, but then they become untestable. So for example, in the late 80s and into the 90s, we had this notion of shaken infant syndrome. And I remember learning about this at the time. We were taught very definitively that if an infant had broken ribs, a subdural hematoma, retinal hemorrhaging, and petechiae, that was just the differential diagnosis. It means the child was shaken. And it turns out over the years, we found there are other reasons for that constellation of injuries. It certainly can be caused by shaking, but it can be caused by other things. Even childbirth can cause some of those injuries. And so, right, the test you'd want to do would be, let's take some children who are injured in that innocent way, and then maybe 100 of them, and then let's shake 100 infants, and then let's compare the results. obviously an impossible experiment to do. Similarly, bite marks has been, very troubled forensic science discipline. Now the latest NIST review, I think rightly says there's really no there. But to do the experiment you'd want to do, you can't get 100 people and bite 100 of them and then take another 100 and injure them in some different way and then begin to look at the marks. It's a very hard experiment to do. But two authors did something very interesting. They took 39 bite mark analysts, 100 case photos, and so that they didn't even necessarily know ground truth, which is normally a bozo no-no in forensic science. But they said, well, let's make an even earlier sort of falsifiable claim. And the claim was, can we even agree? So in forensic science, we'll get to some vocabulary here. We use the word reliable for that, maybe a little different than lawyers use the word reliable. Can the bite mark analyst even agree with what they're looking at, whether or not they're right? And so they were asked a couple of questions. Is this lesion in this photograph, is it a human bite mark, not a human bite mark, or is it suggestive of a bite mark? And what they found is that in only 8% of those cases did 90% of the participants agree across all three questions. And so from the presentation that they gave back in 2016, if you look at the legend on the bottom there, so like if they were all sort of that powder blue, that would mean all of the examiners said, I think this is a human bite mark. So the more color bars you see there, that's the more amount of disagreement. So there's a lot of agreement up here. Almost everybody says, yeah, I think that's a human bite mark. And down here, almost everybody says, no, it's not a bite mark. And in between, they don't even agree if it's a bite mark, let alone is it Jeff's dentition or Marissa's dentition, right? So that's was a very clever way to say we can't do the experiment, the true sort of randomized control trial, bite people and don't bite people, but we might be able to falsify this claim by showing we're not even good at it at sort of a pre-step, right? The other challenge we've had in forensic science is to try to do a validation study that's too big, right? So if we're going to validate something, there are a few questions we have to answer, like what test am I using? What analyte am I looking for? What was my exact procedure? Or if I were trying to investigate gardening, I would want to talk about like, what plant are we talking about? What fertilizer are we talking about? And so we've made the mistake in forensic science to try to say things like firearms and tool marks is valid, right? But in my mind, that's a little bit like saying gardening is valid. Like, well, sure, there are things you can do as a gardener that improve the health of a plant, but everything you do, everything that a gardener says they do works every time, right? And so you realize that these studies are more narrow than some people would like to believe, especially in forensic science, right? So this is an example, like comparison of level butyrol and racemic albuterol combined with ipratropium bromide in acute pediatric asthma, a randomized control trial, right? They have these tortured names of like, we're looking at this one test against this one disease to see how it works, or this one treatment against this one disease. And so that's really important. And it seems like it should go without saying, but here we are. So this is the DEA. Sandra Rodriguez Cruz is a great scientist. I have the highest regard for her. And for those of you that have done cases in the sort of seized drug space, SWIG drug, and now it's an ASTM standard, came out with this notion of, here are all the list of chemical instrumentations. They exist in kind of different categories, category A, category B, category C. And the claim was, as long as you use two things off of category A, or one thing off of category B and two things off of B and C, that your results will be perfect every time. And so they went about trying to prove that. And so they have a sample set of all different kinds of drugs at all different kinds of laboratories being tested with all different kinds of instrumentation. And then they claim that the global accuracy rate, sensitivity is 99.9 and specificity is 99.12. That's akin to saying we've done a randomized control trial and pediatrics is valid, right? You quickly go, what do you mean pediatrics is valid? What pediatric medicine, what procedure that you would do on a pediatric patient? What's the outcome? What are the risks? So this is way too big, right? They're trying to bite off more than they can chew. So I was part of writing a letter to the editors around that, a list of, I'm probably the lowest IQ points and least impressive of the signatories on that paper. But we pointed out several, they've made several mistakes in that. But most notably, like it just wasn't specific enough. Now, this is a good news story. So they responded and said that they agree with those 3 limitations. They thought they'd addressed them. I don't think they really fully had, but it was a collegial response on their part. But the really good news story is Jeremy Triplett, the laboratory director with Kentucky State Police and a drug chemist by training, also a former ASCLD lab president, got a team together, which included Dr. Rodriguez-Cruz at the DEA, and said, let's repeat this study. And this time, let's set it up right. And so we said, okay, we're going to pick one drug, methamphetamine samples, and we're going to very carefully document what is the accuracy for labs that use GC-mass spec, or what's the accuracy if they use IR and a colorimetric test. And we were able to really investigate that issue and then show that, hey, yeah, they're pretty good at it. Not as good as the first paper claimed, but also very narrow, right? For this to be complete, you'd want sort of an encyclopedia where the next chapter is, okay, now we did it with cocaine, and now we did it with fentanyl, and now we did it with LSD, and now we did it with THC. So this is what the kind of specificity, this claim of it can't be too big that you're going for with a validation study. So there's an interesting, after the PCAST report came out, the Department of Justice has a statement on their webpage, and I believe it's still there. I haven't checked in a while. It's an unfortunate statement. It's unsigned, and it's not really endorsed by the Attorney General, but there it sits. And it makes some claims that I don't think are very scientific or very even helpful. And this is one of them. Casework error rates cannot be established through the exclusive and non-severable application of the PCAST experimental design criteria. We'll talk about that in a dozen slides or so. And then they say no single error rate is applicable to all labs, examiner, or cases. Now, the problem with that statement is that it's both, it's true if read properly, that when we do an error rate study, it represents a best case scenario. It's sort of like saying your mileage may vary. If your lab has older equipment or less trained examiners, your rate might be higher. But I think the intent of this statement on the DOJ website was to say, even though this validation study says the error rate's 4%, you don't know how good my lab is. It's probably better than 4. We're probably better. And that's not a supported claim. Validation studies are designed to sort of test the ideal accuracy of a method. So when I read that highlighted part, that almost seems like a stunning admission where it's like, so you're saying that this isn't testable? You're saying that there's no way for us to know a generalized error rate? That sounds like we're drifting back into an untestable claim, right? So I don't think that serves us well as forensic scientists. I wish we would take that statement down. All right, so we have this notion of, is it testable? But then that gets us to the next question, right? Which is, if we think back to our cards, maybe we show that we do better than chance, that as a group, we average 6 or 7 right, way more than chance would say. And so we could claim we have ESP. But you go, well, you don't have ESP all that good, right? And so this notion of, is it testable and does it happen, the thing you're claiming, are you doing better than chance? The next question we have to ask is, well, is the method you're using good enough? And so I want you to think about this. If I said that I had a detector that could detect red cards or anything red, but it only works 52% of the time. But if I said I want to use that in death penalty cases, you would all say that's crazy. But if on the other hand, I said, I want you to fly with me to Vegas, this thing works on roulette wheels. 52% of the time, it will accurately predict if red's going to come up. We'd make $1 million, right? We'd make it kind of slowly, but over playing the roulette wheel, we'd now have a 52% chance of winning, right? So it depends on what we're using it for. The roulette wheel, we maybe need something that works, but barely. If we're doing life-altering, life-changing surgery, we probably want something that works, 999 times out of 1,000. If we're putting people in prison or giving them death sentences, we probably want something that works way better. So how do we find out what way better is? What does that mean? How do we find out sort of this question of accuracy? I love this quote by Wyatt Earp: fast is fine, but accuracy is final. And that really is sort of the coin of the realm for us. So let's kind of figure out what goes into this idea of fulfilling. Does something have a known or potential error rate? So to do that, we got to talk about some keywords: reliability, accuracy, validity. Then we got to delve into what do we mean when I say error, because that's I'm going to define that word very narrowly, and I think that will serve us well. And then as we put all those words into a cauldron and stir, what is a validity study? And then maybe more to the point, what's a good validity study? So first, a few words that I think will help us to kind of get on the same sheet of music. So this idea of validity. So for lawyers, and I see this in the 2009 NAS report and maybe a little bit in the PCAST report, reliability is, you guys have the upper hand on as a scientist. You use it much more like it would be used in a dictionary. Reliable, it means that's something that can be relied on, right? I mean, it's kind of, self-defining. And so what that means to us as scientists, we would substitute that and say, actually, we're going to call that validity. And the reason why is we've hijacked the term reliability, and we use that to mean things where you get the same answer the second time you do the test. Or if Marissa does the same test that I do, we both get the same answer. So that notion, repeatability means me doing the same test on the same sample in a very time limited, and it's like I get the same answer every time I do it. Reproducibility means I do it and then I call Marissa and say, hey, I'm sending you the sample. I want you to do the same thing I did, see if you get the same result. So we're adding a little more complexity to it. So that's often in science, and it's what you saw in the bite mark study that was done. Before I even get to an accuracy study, I could do a reliability study, right? So they did that in a very clever way with bite marks of, it might be impossible to do the accuracy study I want to do. Let's see if we're even reliable, right? And if we're not, then you go, this is just not testable. There's no there. And often you'll see in an analytical chemistry textbook, this sort of chart here that says, how, if I'm collecting data points, if I've got a sample and I'm testing it over and over, or if I got 100 samples and I'm testing them, what are the ways those words compare together, right? So you can imagine if I just, looks like a shotgun shell went off and there's just, I'm trying to hit the bullseye and I'm all over the place, you'd go like, you're not reliable. That's not a tight group and you're not on the bullseye. So that's just nonsense, right? This bottom left is interesting. We don't really do it in forensic science, but some methods are noisy. But if you collect enough data, if you collect enough samples, they will begin to approximate, they will surround the bullseye. And so that becomes important. I could use the average of all those results. The upper right-hand corner is really interesting to anybody who works in a laboratory environment, because that cluster, that reliability is very intriguing, right? So I go, that looks to me like I might have a method that has great promise, and this looks like it could be a calibration issue. it looks like I might just need to figure out how to adjust the sights on the gun, and I can shift everything down to the bullseye. And then we have what we really want. We want that bottom right corner. We want it reliable, a tight cluster, and we want to be on the bullseye. Okay, so and sometimes reliability gets referred to as precision. And then there's two flavors: repeatability, reproducibility. Accuracy, we're going to learn in a second here, comes in two flavors, because in these types of studies, there's two different ways I can be right and two different ways I can be wrong. So just hold that in your head as we move forward here. All right, so what does it mean to make an error? What does it not mean? And to really understand that, we have to do a little more vocabulary. When I think of getting some sort of examination result in a laboratory, I think many of us, and certainly many lawyers I talk to and judges I testify before, we want this simplified concept, right? That you got a result and hey, it's either right or wrong. And that's certainly a true statement. But I think it's not a complete statement, and it comes with some problems. And so especially in pattern matching disciplines, I want you to consider a couple of these problems. The first is it kind of forces the examiner into what some statisticians call the fall off a cliff, jump off a cliff moment, right? So if I'm looking at these two fingerprints, or I'm looking at these two cartridge cases under a microscope, and I'm thinking, you know, I see some areas of dissimilarity, but I see a lot of similarity. Gosh, I see there's more similarity. I feel this like I'm approaching this cliff. Do I jump and say it matches, or do I hold back? And there are many other places in science where we don't require that binary decision. We let people comment directly on, here's the concentration of the analyte I was testing. Here's the amount of similarity I detected, and then I can give you some sort of probabilistic statement about the chances that they're from the same source, right? Based on seeing this amount of similarity. The other problem this has, and I've seen throughout my forensic science career, is especially in pattern disciplines, latent fingerprints, question documents, firearms and tool marks, where the examiner is both the sort of technician who's preparing the samples, but they also become their own instrument. They are the detection apparatus. If they reach a wrong decision in this concept, then we feel like they're a racehorse that's broken its leg. They can never testify again. They've got to be remediated. It's this huge problem. And what that leaves out is maybe they didn't do anything wrong. Maybe that sample that was actually a non-matching pair shared many, many similarities. So many similarities that if you properly applied the method, you would reach the conclusion that it matches. That's the conclusion you're supposed to reach with the method that you have. So this oversimplification creates those two problems. How do we fix that? So I think the real way to think about an exam result is first, like as a former lab director, the first thing I would look at is this work that was done by my examiner conforming or non-conforming, right? So non-conforming, you can think of those, I call them the M words. They might have made some sort of mistake, right? They might have swapped the sample out, or they might have grabbed the wrong reagent. And they thought they reached for the hydrochloric acid and they picked up the hyperfluoric acid by mistake. They wrote down a number and transposed two of the numbers, right? So those are just mistakes. Malpractice could be, right, I was put on the job and I'm not very good at it. I kind of got lucky and passed a competency test. And now I'm testing for cocaine, but I'm not very good at this. I'm messy. I don't read the chromatogram very well. I don't understand what I'm doing. And the final one, misconduct, much harder to detect, right? Especially, but sort of this notion of dry labbing. I know what I'm doing, but I want to go fishing this afternoon. I've got these 50 bindles of white powder, and I go, if I just say those were all negative, I don't have to write a report. I can go fishing. Nobody goes to prison. Like maybe I'll just do that. So the important thing about all of these M words is that they're detectable, right? People can, the things we do in labs, proficiency testing, technical review, a verification step where a second examiner comes in. They're all things that can be uncovered. Admittedly, misconduct's the hardest one to uncover because I might be taking steps to cover my tracks. But those all share that they can be part of an audit, right? On the other hand, my examiner hopefully did conforming work. We look at it, the verification step, the technical review, every I is dotted, every T is crossed. They use the right chemicals. Looks like the instrumentation performed correctly. And most of us would say, okay, well, then we're done. That means that it's accurate. But what I want to sort of insert into this conversation, really important, is that's one of three things that could happen. The other two things are I could have a false negative error or I could have a false positive error. And this is where I like to delineate these words, that I very carefully with my students say, let's reserve the word error for this situation with conforming work and save the word mistake for this situation of non-conforming work. The English as a second language teaching community, interestingly, makes the same delineation. So they talk about if I'm, saying the sentence in English and I've just learned it and I make a mistake, I hear it. I might even correct myself and go, I didn't conjugate that verb right. I can hear it. Or my fellow students hear it immediately. And I know it was a mistake. An error, on the other hand, is maybe the teacher even taught the grammar wrong. I learned it wrong. My fellow students learned it wrong. And when I say it wrong, they all nod their head and go, that sounds right to us. And so in that crowd, in that cohort, that error now is undetectable, right? It's not auditable. It's not like a mistake. Very important. Often I hear in admissibility hearings when the examiner is trying to establish that, hey, we're accurate, we don't have errors, that a large part of their presentation is about the things they do to make sure their work is conforming. And so I'm there to remind the judge of all of those things are great and should be done. They help limit mistakes, malpractice, and misconduct, but they don't do anything to improve the error rate. The only thing that improves the error rate is a better method, a new and better method. So when we talk about a validation study, this is the area we're in. We're assuming that the work was conforming. We're giving you the best case scenario. What are the limits of the method when employed perfectly? In PCAST parlance, they recognize this, and so they came up with the phrase foundational validity, and they meant for this sort of conforming work, and then validity is applied. And so this gets back to that statement on the DOJ website. I might show through my foundational validity that there's a 1% error rate. The mileage in my lab might vary. Maybe I have less experienced examiners. Maybe I have bad equipment. Maybe my error rate is higher because I've baked in some mistakes and malpractice that I'm not catching on the audits, right? So important concept. Others have recognized it. So you might hear, if you're getting a PCAST presentation, you won't hear conforming and non-conforming. You'll hear foundational validity. Validity is applied. Okay, let's do this one more time. So humor me. I won't make you put it in the chat, but I want you to take one more set of guesses just so you can kind of look down at what you did. But I'm going to change it from our first test, right? So the first test I just said, tell me whether it's red or black. Now I want to make it a little more like we would see in a diagnostic environment, right? Where we're trying to diagnose something in a clinical medical setting or in a forensics lab. The diagnosis might be these two things match, right? Or I'm diagnosing this thing, I'm categorizing it as cocaine or methamphetamine. And so if we say, I've got this method that will detect red, it will detect the positive for red condition. So I want you to take your guesses, and then let's talk about what each of those mean. And Marissa, I'll pause for a second. I see there's still a few chats there. Are there questions that I just bulldozed past that I should?
No.
Okay.
No, they're not. I just would ask just to repeat what you're asking us to do, just in case folks zoned out for a second.
Yeah. So just take a look at the cards, and I want you one more time to similarly to detect if it's red or black, but this time I just want you to go, hey, it's, put a red or a positive sign for any card you think is red on the underside, and a negative for any one that you think is black. And I'll trust that you've done that. As I said, I won't make you actually type in your numbers, but there are the answers. Okay, so by adding that complication, by making it more diagnostic, where I said, I want you to tell me where you detect red cards, we've now made the accuracy determination a little more complex, and I think in a really good way. And so what we realize is there's two different ways for me to be right, and there's two different ways for me to be wrong, right? I could accurately detect that there's a red card there, and I could also accurately detect that there's not a red card there. And then the two ways I could be wrong is I could say there was a red card and it turns out that it was black, but I could also say there was a black card and it turns out that it was red, right? So those notions are very important, and it makes these validation studies, we have to look at these samples now, like it looks like one big sample of 10 cards, but in my mind, it's really like, it's got two subsets in it that are really important and kind of apples and oranges, right? So I've got 6 opportunities here to identify a black card and 4 opportunities to identify a red card. And so in this world, we've got some special names to capture that. Sensitivity is my ability to correctly identify the red card, the way I've conceived of this test, right? I've said this is a red detector. That's the test. So the sensitivity is how sensitive am I to picking up, making sure I find all the red cards. Specificity, on the other hand, is how good am I at avoiding calling a black card a red card, right? So in our test, there were 4 opportunities to measure my sensitivity and 6 opportunities to measure my specificity. That's really important. So you could imagine, right? There are a couple ways to thwart this test. And so I've seen this happen in real life. I want you to imagine what would happen if I just guessed that every card was red. If I guessed that every card was red, I could, in a very disingenuous way, say, hey, the sensitivity is 100%. I would get all 4 of those right. I would say my accuracy is 100% and sensitivity is 100%, right? And so ironically, I remember my time as a chief scientist, there was a vendor selling something called X-spray. And it was a spray that soldiers could take into the battlefield. If they encountered something they thought might be explosive, they would spray this material on it and it would turn red in the presence of explosives. Now, there's a lot of different kinds of explosives. There's like TNT, there are gunpowder derivatives, there's fuel oil derivatives, there's all kinds of very different chemical structure. And so they set up a display for a general and sprayed this X-spray on all these different chemical compounds, and it turned red on every single one of them. And so I had the unfortunate opportunity to remind the general that red spray paint would do exactly the same thing, right? What's missing from that test is how about some, cake mix and some baby powder and, some cooking oil and some, ground up aspirin, right? There's all kinds of things that we should say, you've got to put black cards in the mix since we need to measure both of these things. All right, so if these were my results, it looks like, hey, I got 3 of the 4 red ones correct. So my sensitivity would be 0.75. And it looks like I got 5 of those black ones correct, but I called one of them red. So my specificity would be 0.83. And then we sometimes, because sensitivity and specificity are hard to remember, even for scientists who are not in this space, they have to kind of remind themselves which one's which. For non-scientists, like I don't encounter those words, I don't understand. So we can use more common words and say, hey, the false negative rate is 1 minus the sensitivity. So in this case, we'd say, hey, the false negative rate, you're going to misread things like 25% of the time. And the false positive rate would be 1 minus the specificity, or you could say about 16, 17% of the time, you might have a false positive result with this test. There's some pretty authoritative writing on this. This guy, John Sweats, is kind of the godfather of diagnostic testing. And so it's a pretty easy read and it outlines all this. There's a great Wikipedia entry on this sensitivity, specificity, and kind of this notion of diagnostic testing largely based on this article. But I offer that to say this isn't something I just thought of for this presentation. This is how this community thinks about these things. And so we often will see in validation studies a figure that looks like this. What did the examiner predict, positive or negative? And then what were the actual ground truth values, positive or negative? So if I predicted positive and it was positive, that's a true positive. And the diagonals become important then, right? If I predicted negative and the actual value was negative, that's a true negative. And then those off diagonals are where my false negatives and false positives live. Very important way to think about this. Okay, so how do we use that to make a validation study? And then really, what's a good validation study? So to lay the stage for where we're going to head next December, the firearms and tool marks community, kind of pre-2009, right? They had on their website, the AFD website, that there's a wealth of literature that demonstrates that this has been critically studied and it's to the precepts of the scientific method. And so, and it's culminated in the AFD theory of identification. We'll talk about that. It's got some real challenges. So that's where they were. We have a wealth of literature. In 2008, there's an NAS report, not the NAS report as we sort of colloquially refer to it, on ballistic imaging. And the point of that report was not to look at the validity of ballistic imaging. It was to look at the feasibility. Could we have a nationwide database for ballistic images, similar to maybe CODIS with DNA? But as a part of that effort, because this was, populated, the authors of this study, by some mainstream scientists, they got curious and said, hey, I'm kind of curious, where are the validation studies for this? And so they just almost noted in passing the validity of the fundamental assumptions of uniqueness and reproducibility of firearms-related tool marks has not yet been fully demonstrated. So they didn't say, we think this is garbage. They just went, we can't find the studies that we would normally expect to see. And then in 2009, the NAS report, as we call it, the NAS report, that always makes me chuckle because they read a lot of other reports about a lot of other things. But they note sufficient studies have not been done to understand the reliability and repeatability of these methods. And here again, this is an example where they use the word reliability there. I think that's the lawyers and judges. The scientists would have said validity there. So then in about 2012, there's something called the Subcommittee on Forensic Science. It was a precursor to the National Commission on Forensic Science. We put together some annotated bibliographies. I served on that committee. We went out to places like AFD and Swig Gun at the time and said, what is that wealth of literature that you're relying on? And so we collected that and we said, well, will you annotate it for us? Like, here's the citation, and what do you think that actually says? That committee sunsetted before we could do what I had hoped to do, which is sort of read those and give them a letter grade. But in 2016, that's precisely what PCAST did. They picked those up and said, we're going to read those and see, like, do they look like a validation study we would expect in any other mainstream science? And we find that many of these earlier studies were inappropriately designed to assess foundational validity and estimate reliability. And so, so how'd that happen? How do we have a situation where the firearms and tool marks community thinks they have a wealth of literature, and then the larger scientific community says, we're not seeing what we're looking for? And I think part of the problem is, if you look at the AFI journal or the New England Journal of Medicine, for that matter, not every study in there is a randomized controlled trial or a validation study, right? There's all kinds. There's case studies and descriptive research and cohort studies and phenomenology. Like, we just want to understand better how striations are left on a bullet. We want to understand how this metal registers the marks compared to that metal. Those are all very important studies, but they are not a substitute, and a dozen of them don't become a substitute for the actual properly designed validation study. The other thing that does not inform foundational validity, right, we touched on this earlier, are any of those things that would help with non-conforming work. Proficiency tests, performance checks, right? And then we talked about the phenomenology studies. Sadly, sometimes, right, I've heard people talk about the reason we know this works, or here's a history of early cases where the judges put someone in jail and we solved the crime. And so what's really painful about a claim like that is you didn't have any ground truth. You hope that you're disciplined. You hope that firearms and tool marks solved that crime and the right person went to jail. But that's the fact that it was used that way doesn't mean it was properly used that way. So the wheelbarrow doesn't help. The proficiency tests, things that help be conforming, don't help. And the other thing with this notion of a wealth of literature, I'm struck that when Einstein first came out with his general theory of relativity, there were a group of authors, physicists, who were just, unbelieving. And so they published this little pamphlet that was 100 authors against Einstein. And he replied, why 100? If I were wrong, one would have been enough. And I think that sentiment is sort of what mainstream scientists look for. If you're claiming something's valid and you're like, and we have 100 studies, they would sort of chuckle and go, well, that sounds like a waste of money. Like, why not one or two? Like, so what PCAST said is maybe one's not enough. You want to have someone else replicate that study, make sure they got a similar validation error rates, that they got similar metrics. But there's no reason to have a wealth of studies. You want a handful of very well-constructed studies that have results that are reasonably in concordance. All right, so I think we're right on time to sort of finish this up and leave some time for questions. Then what is it that makes a good validity study? And why would PCAST be able to look at the old studies and go, these aren't quite right. That's not what we're looking for. So let's talk about those key ingredients. So for me, for the typical, if I'm thinking of firearms and tool marks or fingerprints, or for that matter, methamphetamine, there are a few considerations I'm going to have really early on. The first thing is we're going to have samples that we prepared, right, to give to the examiner. So those are either pairs of fingerprints or pairs of cartridge cases or pairs of bullets or a bag that has white powder in it or off-white powder or whatever thing that they're going to test. So what I've got to consider about the collection and kind of curation of those samples is I've got to meet with my friends at CSAFE, the statisticians, and say, hey, how many of these samples do I need? How many cards do I need in my deck before I could really say, I think these people have ESP? If they get 4 right, is that okay? Or do they need to get 4,000 right? And there's a trade-off there, right? The statisticians would say, well, the more the better. But lab directors would go, look, I don't have endless resources. So what's a breaking point? What's a good number that will give me results that I can count on? The size, the provenance is really important, right? Ground truth is really important. So sadly, firearms and tool marks is guilty of this. Some of the studies, the ground truth, the reason they said this is a ground truth matching set of cartridge cases is because an examiner had previously looked at it and said they thought it matched. And so I joke with people and say, you can't use the thing you're trying to test the thing you're trying to use, right? There's something too circular about that. So, in a firearm setting, that would mean I go to the range, I take the gun, I load it, I fire 2 cartridge cases, and I bag them together, and I document, and I have this, clear, traceable history that these were witnessed to have come from the same gun. And then how I give those samples to the people in the study are important. So we'll talk about this idea of an open set, where the way they're presented, the samples, is very similar to how they would see it in casework. And there's no way that I interfere with the test and somehow make it easier as people participate. We'll talk about that in one slide more in a little more detail. The second ingredient, right, is there will be people who participate in this study. And so similar to the number of samples, right, I probably just don't want my favorite 4 drug chemist are my favorite 7 firearms and tool marks examiners, right? So I need a reasonable number of those. And I want to probably get some demographic information, maybe their experience level, maybe their education level. And then I want to keep track of completion rates, right? Because some of these participants may drop out, right? So you can imagine a drug study where I've got a drug that kills 30% of the people, but makes 60% of the people well. And I get to the end of the study and I go, look, it made all 60 of these people well. But I haven't factored in, no, 30 of them dropped out of the study because they died, right? So that's the most extreme example. We'll see next month when we look at some of these farms and tool mark studies, there's significant dropout, maybe for some very innocent reasons, but it can have a profound effect on what we understand about the results of those studies. And the final thing is how the results of the study are reported are very important. And so what the scientists, the sort of mainstream scientists in a group like PCAST are looking for is it should be very straightforward, strikes and balls, traditional accuracy metrics. So things like sensitivity, specificity, true positive, true negative, false negative. Those are sometimes displayed in something called a receiver operator characteristic curve or detection error trade-off curve. Those are just ways of graphing those results that are more common on the scientific side. And then we need a very rigorous handling of what do we do if a participant says, I want to call this sample inconclusive, right? So that's going to feature very heavily in our discussion next December. And so we have to be very clear how we're going to handle that. And then we also, anything we're measuring, so in this case, we're measuring an error rate. So the error rate, it would be wrong for me just to measure anything as a physical scientist and say the answer is 10 centimeters, 10 false positives per 1,000, 10 miles per hour, breath alcohol of 0.08. I've got to say 0.08 plus or minus 0.005. So this plus or minus part is also really just fundamental to how scientists report things that they have measured. So that's an important part. PCAST in the report and what they labeled box 4, it's kind of hiding 2/3 of the way through the report. They came up with these 6 criteria that I think the DOJ statement calls something like non-severable, but those are all basically kind of what I said about each one of those things that we're looking for. Those are very straightforward. Those are not onerous at all. In fact, there it is, the exclusive and non-severable application of PCAST experimental design criteria. So it raises the question, was PCAST just too hard on us? And I would suggest that they were actually a little bit easy on us, right? So the gold standard is something called a randomized control trial. A meta-analysis would be like you've got 4 or 5 of those with similar results. And so you have a group of scholars get together and go, can we see trends among all 4 or 5 of these really well-done studies? What we did is more of a cohort study. We'll talk about why in a second. And where we normally were, kind of the stuff that AFDI had presented to PCAST, was down here. So not only was PCAST not too hard, I think they gave us a pass. I think they said, we understand to do this, the study we really would want you to do might be impossible. And so let's talk about why. What would be the study we'd really want to do? And that would mean that in diagnostic testing, we'd want to do something called a blind study. Now, this also gets really misunderstood by forensic scientists. We will talk about single and double blind studies, and that's a completely misappropriate use of those words. So single and double blind refer to treatments in a hospital, not testing in a lab. And so single blind means the patient doesn't know they got the placebo or the real drug. Double blind means their caretakers, physicians, med techs, nurses also don't know. We don't have that set up at all in a diagnostic test. What we want, and what PCAST would want, the top end of that pyramid would be test blind. And test blind would mean not only have we done all those other ingredients that I talked about, the right sample size, they're realistic, they're good, we've got a good number of participants. It would be that the examiners, when they're participating in the validation study, they don't know. they think they're working on real casework. That would be ideal for a lot of reasons, and we could talk about in the Q&A or some next month as well. That's almost impossible to do in any large, it's almost impossible to do at all. Maybe completely impossible to do on a large scale nationwide. So test blind would be what we really want. PCAST went, well, we don't think you can do that, so we'll settle for the best that you can do. Other reasons that study design can be so hard. I'm going to just, the birthday paradox is a great problem. I'm going to skip through a couple of those. The Monty Hall problem is a great problem, very interesting. We can tackle, or I can take a phone call from any one of you over the week if you want to talk through these. The two daughters problem, maybe even more provocative. If you got 1,000 families, we curate them at random, they each have 2 children. And now I say, stand up if you have at least $1. So everybody stands up that has at least $1. And now I ask of the people standing, what's the chances that their other child is a girl? And for most of us, you feel like, well, it's got to be 50-50, right? I mean, I just kind of stood up at random. You just sort of randomly said, if you have at least one girl, stand up. But it turns out that by me just tinkering with my initial random collection of people a little bit, I profoundly changed who stood up, right? So if I say, here's all my people, so you could have 2 daughters, a daughter and a son and a daughter, or 2 sons, and I say, stand up if you have at least 1 daughter, these people stand up. And then if I say, what are the chances that your other child is a daughter, the chances go way up, or the chances change, right? The chances that the other child's a daughter now is just the 1/3, right? And so it changes just by me tinkering a little bit. So where that comes into play is the early studies that were done by Jim Hamby were this sort of closed set design, right? Sends up 10 barrels, are known pairs of cartridge cases from 10 barrels, and then some question samples. But it gives the instruction that the unknown set of 15 bullets was comprised of at least 1 bullet from each of the barrels and no more than 3 bullets from any one barrel. With that little bit of information, you now constrain how these things can match up. You make it more like a crossword puzzle. And so that becomes really tricky. So let me just show you a brief bit of math here. In our detect red exercise that we did together, I bet many of us assumed that there were 5 red and 5 black, because that's kind of how I did the first test. I kind of mixed it up by making it 6 and 4. I want you to think about what would happen if I gave you the test again and I said, try to guess, but I'm telling you before you start, there are in fact 5 red and 5 black. So if I don't tell you that, that's called an open set. And that means every card could be red, every card could be black, it could be 9 and 1, 8 and 2, 2 and 8. And that means if you do the math, there's 2 raised to the 10 power ways to arrange red and black cards, or 1,024 different ways that I could present these cards to you. So that means for you to guess correctly, the chances of guessing correctly on accident, 10 out of 10 would be 1 in 1,024. If on the other hand, I say, before you start, there's 5 red, 5 black, to statisticians, they have a fancy way of saying that. They go, that's a condition where we would use the words 10 choose 5. And they have this binomial coefficient. Don't be afraid with the hieroglyphic looking math. You can trust me on that. But if you do this calculation, these factorials, you get 252. And it says, so the moment I say, hey, 5 have to be red and 5 have to be black, there's not 1,024 ways to arrange the cards anymore. There's only 252 ways to arrange the cards. So with just that one little blurb out of my mouth, I made the test about 4 times easier, right? And it wouldn't intuitively seem that way. All right. So many times we've got forensic scientists getting on the stand, trying to offer why their things are valid, sometimes with very dated sort of admissibility resource kits, slides that have been used over and over, that now for, since 2016, PCAST went, those are not very compelling slides. So we've talked about testability. We've talked about known or potential error rates, what it will look like. Next week or next month, we're going to talk about what happens when firearms and tool marks meets these Daubert standards. And to do that, we'll talk about the AFTI theory of identification. We'll do a little review of the literature, talk about their weak studies or better studies, their known or potential error rates, and then what are the unresolved issues? What's being contested and debated right now? So I think that leaves a small handful of minutes for questions, but I'll stay on as long as anybody would like me to.
And we appreciate that, Jeff. Thank you so much for all of this. And if you have a question, please put it in the chat for Jeff. I mean, I think, Jeff, my initial question is kind of like, okay, so I have this, study in front of me, and I'm trying to decide, what was used at trial, does it have validity, does it not have validity, and am I looking at that PCAST list that you had a few slides back to kind of, is that like a checklist for me to be able to kind of determine whether this is a good study or a bad study, and whether I can use that when I'm trying to figure this out?
Yeah, that's a great question, and Marissa, I think a great approach. That's how I do it. If a new study comes out, I sort of use that checklist. There's some shortcuts, right? I can just begin to look very quickly for, hopefully these numbers are not obscure. Like, is it really easy to find how many people participated in the study? Is it really easy to find how many samples there are in the study? And more importantly then, right, we said there's kind of two sets of samples. How many ground truth negatives were there? How many ground truth positives were there? Is it really easy to deduce what were the accuracy metrics? So I just I look for those immediately. And if 30 minutes later, I'm like, I'm having a hard time finding those, then my index of suspicion starts raising. Is this going, how's this study faring? The other thing is, although in the long run this is dynamic, in the shorter run it's a little more stagnant, right? There is now a bibliography of studies, and so for firearms and tool marks, we'll present those next time. What are the post PCAST studies, sort of what I call them, that kind of meet the PCAST criteria, and which ones are not? And so then you're just sort of adding, as a new study comes out, you're trying to determine, did it earn its way on to the list?
So is that an easy kind of dichotomy there? Is it pre-PCAST or post-PCAST? PCAST?
Yeah, I think so. So to the firearm tool marks community's credit, the studies that have come out, there are one or two exceptions. We'll talk about those, but most of the studies that have come out from that community since then have met that criteria. And whether they were, one was done by a guy named Kiesler out of Indianapolis, published, he's a firearms and tool marks guy, lab director there, published in the AFTI journal, right? One was done by a PhD scholar out of Arizona State University, published in the Proceedings of the National Academies of Sciences. But from when I read them, I go, no, they both meet the PCAST criteria. So it's relatively straightforward. That's less of the debate, with one or two exceptions. The bigger debate is, even for those better studies, what are their limitations? And are we overstating the accuracy, or some of us overstating the accuracy based on what those studies reveal?
And I'm not going to ask you for that answer, because I know that we're going to have that next month. So
yeah, that's the whole talk.
And that's the whole talk, right? So for those of you who are obviously paying attention, for next month, this is what we're going to be getting into, is kind of talking about some of those studies that are out there, particularly for firearms and tool marks, and determining how we can kind of use those for looking at the evidence that you have to look at, particularly if you're in a situation where you need to get retesting done. And what does that mean for you? What kind of testing should we be looking at? And how can you test whether it is reliable and accurate, as Dr. Salyards was saying? But I don't mean to monopolize the conversation, looking in the chat just to see if there are other questions. And since we're not actually able to launch the poll this month, so you have a month break from that, but I do want to let folks know about what's coming up. So on December 3rd, if you missed it, the NRE, the National Registry of Exonerations, will again host their webinar on how to navigate their new website. Of course, Dr. Salyards will be back with us again in December on the 10th for part 2 of understanding known or potential error rates, and then focusing in on the firearms and tool mark studies. And then in January, we go back to DNA with Dr. Angeli Ronanive, with serology and early DNA platforms. And then in February, if there's anybody from Indiana on this call, you are up. We're going to be talking about a case study from Indiana of a collaborative exoneration with the Conviction Integrity Unit and the Notre Dame Innocence Organization. So checking again in the chat, seeing no questions. Okay. Dr. Salyards, anything you want to leave us with as a prelim for next month?
No, thank you so much. I look forward to getting to talk more with you next month.
Okay, so thank you everybody for joining.